welcome to The Explainer. Today, we're diving into a huge medical mystery. But our main tool isn't a microscope, it's pure math. Yeah, you heard that right. We're going to uncover a hidden law of the universe that could totally change how you think about one of life's biggest, scariest questions.
You've probably wondered this yourself, right? Is getting cancer just random bad luck, a roll of the dice, or do our choices actually matter? I mean, this has been a huge debate for decades, but what's so cool is that the answer might have been hiding in the numbers all along.
All right, so to get into this, we have to start with a really weird puzzle. Let's call it the cancer clock. For the longest time, scientists noticed that different cancers tend to show up at specific ages, almost like they're on a schedule, but nobody could figure out why. What was this clock? You know, the old way of thinking was pretty simple. Getting older means a higher cancer risk. Makes sense, right? Well, it's not that simple. Actually, it's kind of wrong. When you look at the real data, something much weirder is happening. For a lot of cancers, the risk goes up, peaks, and then it actually starts to go down in old age. The old models just couldn't explain that at all. They were totally broken.
Okay, so fast forward to 2017. A researcher comes along with this just wild idea, a total game changer. They thought, what if we're all looking at this the wrong way? What if this isn't about biology? What if this curve we're seeing is just pure math?
Okay, so take a look at this. This is what you get when you plot real cancer cases against age. It's a mess, right? It's all over the place, super noisy, totally scattered. It looks completely random. How could you possibly find a pattern in that? But check this out. Watch what happens when we overlay one specific mathematical formula on top of it. It's called the Erlang distribution. Boom! Just like that, all the chaos just disappears. This curve cuts right through the noise and reveals this incredibly clean, almost perfect pattern that was hiding there the whole time. And I'm not just saying it's a good fit. In statistics, a perfect 100% match is a score of 1. Well, across 20 of the most common cancers, this model scored, get this, an average of 0.995. That is just insane. You almost never see a number that clean in biology. It's an unbelievably precise match.
Okay, this is where it gets really, really interesting. This Erlang curve isn't just some random line that happens to fit. No, it describes something very real. It's the mathematics of a waiting game. Imagine you're waiting for, say, 3 different buses to arrive, and each arrival is random. This formula predicts how long you'll probably have to wait for all 3. It's the math of waiting for a certain number of random hits to accumulate.
So what does that mean for cancer? Well, this model spits out 2 super powerful numbers for every single cancer type. First, there's K. That's the number of critical hits, or mutations, a cell needs before it turns cancerous. Then there's B, which is the average time between each of those random hits. So simple, but so powerful.
This was a huge deal for understanding adult cancers, but you gotta ask, was this just a fluke, a really lucky coincidence, or was this something bigger, like a universal law of cancer that works for everything?
So to really stress test this idea, researchers decided to throw the ultimate curveball at it. Childhood cancers. I mean, their patterns are completely different. They often peak super early in life. If the model could explain these, then they might really be onto something huge.
And this is where it gets just brilliant. All the other standard statistical models, they totally fell apart. To even try and fit the data, they started spitting out biologically impossible answers, like predicting that a cancer started at a negative age, like before the kid was even conceived. It was nonsense. But the Erlang model? It was the only one that fit the data for every single childhood cancer perfectly, without any of that impossible stuff.
The conclusion from this was just, wow. This mathematical pattern, this waiting game, wasn't a coincidence. It really looked like a fundamental, universal law for how all cancers work, from the ones in the very young to the ones in the very old. Okay, so we've established this universal math behind cancer. Pretty cool, right? But this is where the story takes a turn, from being all about abstract numbers to something really practical for you and me. And that's all thanks to a 2022 study that asked the next logical question. But first, let's get a term down. Anthropogenic risk factors. It sounds complicated, but it's not. It's basically all the preventable, man-made stuff that can increase cancer risk. We're talking about things like smoking, air pollution, a bad diet, stuff that's part of our modern world, not just our basic biology. All right, so the researchers asked this amazing question. They said, okay, we know some cancers need a lot of hits, that K number, and some need just a few. Is there any connection between that number and the percentage of cases caused by all that preventable modern lifestyle stuff?
And the answer was, whoa. For cancers that are linked to more natural things, like viruses or just sunlight, there was no pattern. It was random. But, and this is the key, for the cancers that are tied to those anthropogenic, modern lifestyle factors, the connection was a perfectly straight line. The more hits a cancer needed, the more it was linked to our lifestyle.
So what does that mean? It's a huge deal. The math basically proves that cancers requiring a whole bunch of hits to develop are much, much more reliant on getting those hits from the outside world, from our environment and our choices.
And that right there brings us to the big takeaway, the most important part of this whole thing. This math isn't just some neat academic exercise. It actually gives us a whole new way of looking at our own power when it comes to prevention.
Let's go back to that analogy of a locked door. Imagine a cancer that only needs, say, 2 keys to unlock it. Well, a cell can make a random mistake when it divides, and boom, there are your 2 keys. That's what we mean by bad luck. It can just happen.
But now, imagine a different cancer that needs 20 keys to unlock 20 different locks. The odds of random chance providing all 20 of those keys in the right order? It's practically zero. So for that cancer to even get started, it needs a constant supply of keys from the outside. And those keys are things like smoking, pollution, and a poor diet.
This table just makes it crystal clear. Let's take lung cancer. The math says it needs about 24 hits or keys. And look at this. A whopping 82% of cases are linked to preventable factors. Now compare that to a certain type of brain cancer. It only needs about 9 hits, and the preventable fraction? Basically 0. That's a cancer that is almost entirely driven by bad luck.
So the math gives us this incredibly clear picture. Look, bad luck is always going to be part of the equation. We can't eliminate risk completely. But for so many of the most common cancers, the ones that need that long chain of keys, the game isn't just a lottery. The odds aren't fixed. We have this amazing ability to influence the outcome, to stack the deck in our favor just by cutting down on those external risk factors.
So, at the end of the day, this hidden math doesn't tell us our fate. It just tells us the rules of the game. It shows us the odds. The real question this leaves us with is, now that you know the odds, how is that going to change the way you play the game?